So we are starting the next unit, which is meteorology. Meteorology is the study of weather and our atmosphere, one of the zones on the Earth, along with the land, the air, space, water would be the other zone, and then you got space that you've already studied. With meteorology, we're segueing from what you learned in astronomy, dealing with seasons and the reasons for the seasons. The fact the Earth is tilted 23.5 degrees, that tilt causes the sun to unevenly heat the Earth. Well, because you have an unequal heating of the Earth, you're going to have zones on the Earth that are hotter, you're going to have zones that are cooler, and because of that, you're going to have different types of weather and eventually different types of life, which would be an ecology idea, which you're going to study later in the year. So it all gets connected. All these units connect together, and that's why we're doing meteorology at this time. Meteorology is the study of the atmosphere, and it's going to be study of weather, because that's where weather exists, or it takes place. It takes place in the atmosphere. So this whole unit, we're going to start the unit with talking about the atmosphere, and then we'll get into talking about water in the atmosphere. And from water is what's going to lead us to our basic discussions of weather. Before I started into the notes, I gave students a layers of the atmosphere activity to complete. So before you continue with these notes or this recording or this movie, make sure that you do the activity. It's a graphing activity where you, by data, are going to sort out the different layers of the atmosphere based on temperature. And there's a couple questions that I'm going to keep referring back to throughout these notes. That's why the activity becomes important. So if you have done the activity and you're ready to continue on, so then you can listen on to this video. Keep this in mind. As we begin to discuss the layers of the atmosphere and how it relates to weather, use the activity that we did or you've done previously to answer these two following questions. The question one being, how does temperature change as altitude increases? Now, altitude is how high off the ground you are. So the higher or the farther away from the ground you go, the higher in altitude something is. So that's what altitude is going to be. So how does temperature change as altitude increases? And then what would make a good relationship statement to make for temperature and altitude? What I mean by that is, what's a statement you can make that's always true that has to do with both temperature and altitude? Like, for example, when we talk about water later in the year, we're going to say as you go deeper in water, pressure is going to get greater and greater because there's more water molecules being pulled down. So the relationship question is, or statement is, as you go further down in the water, the more pressure there is. That's a relationship question. So I'm asking you to think of, just think for now, what would be a good relationship statement to make for temperature and altitude? So the higher you go in altitude, what's it do to the temperature? The lower you in altitude, what's that do to the temperature? And is there a difference? Before we can answer those two questions from the previous screen, and we will answer them later in this slideshow, we need to first talk about what is our atmosphere. So I include a picture of the Earth. The land of the Earth is what you see, because you see right through, if you look at any pictures from Earth from space, or to Earth from space, you see right through the ground. You kind of see through the atmosphere, unless there's clouds. Clouds are the only indication that there's something else above the ground that you can see. So this picture is a good representation of what the atmosphere is. So what is the atmosphere of the Earth? Pretty much, it's pretty simple. It's a mixture of gases that surround the Earth. So around you that you're seeing through a bunch of different molecules of gas. I'm not going to talk about which molecules you're talking about. Yeah, we're going to talk about that in a little bit, but that's what it is. It's primarily a mixture of gas that surrounds you and it surrounds the Earth. And you're always walking through an atmosphere. You need atmosphere to survive. It's the only way we breathe on Earth. We need that atmosphere. And even when you go into other rooms and go into buildings and closed spaces, there's still an atmosphere there. So what is it? It's this mixture of gases. When you were in chemistry in 7th grade, you learned that the atmosphere, or air, is a mixture, but you also learned that it is matter, because it's something that has mass and takes up space. The atmosphere takes up space and has a mass. We're going to start talking about pressure, talking about the number of air molecules that are in a certain location. Now, the other question there says, how does the atmosphere of the Earth protect us? We've talked a little bit about this in astronomy, but there's other ways the atmosphere protects us. First of all, it contains the oxygen we need to breathe. So we take in oxygen as animals, we take in oxygen, we convert it to carbon dioxide, and we exhale carbon dioxide. Plants will then take that carbon dioxide, make food, and release oxygen back into the atmosphere. So plants and animals have a very good, what we call a symbiotic relationship to that we need each other for survival. How else does it protect us? Well, it protects us from harmful UV rays of the sun. As we start talking about the layers of the atmosphere, there's one layer that contains a protective shield for us called the ozone layer, and that actually protects us from the very dangerous ultraviolet radiation that can come from the sun. Ultraviolet radiation is what causes skin cancer if you have too much exposure to the UV rays of the sun. So that's why we always say, or maybe your parents always say, when you go out, you're going to be out at the pool, or you're going to be outside for an extended period of time, you put sun lotion, sunscreen on to protect yourself from those dangerous UV rays. We also studied in astronomy, that's why I put the connection there, that it also protects us from meteoroids, because we have space rocks that are pulled from the Earth's gravity into Earth all the time. The atmosphere, that thick atmosphere we have that surrounds the Earth, actually protects us from these flying objects and helps to burn up any rocks that are smaller than 10 meters completely up. It disintegrates the meteor that's entered. If it's big enough, it strikes the surface, obviously, but we wouldn't want that happening on a regular basis where space rocks are flying at an extremely high rate of velocity and striking us on the Earth. So the atmosphere actually does help protect us from that. So this graphic on this page has no labels, and I did that on purpose. The quantities of each section, each colored section, are accurate, but I left the labels off on purpose to give you an idea of the molecules that make up our atmosphere. And you may have learned this in elementary school. I'm just making sure we have a reconnection to it here. There are certain gas molecules that take up our atmosphere, that make up our atmosphere, okay? And I know we just talked about the need for oxygen. So oxygen is obviously going to be one of the molecules, but there are other molecules that make up our atmosphere. So what I was going to do with the class is kind of do like a Family Feud type of thing. This is the question, your top 5 answers are on the board. Okay, what gases make up our atmosphere? Now, you probably want to say oxygen is the number 1, which means oxygen, since we use it so much, oxygen must be that big layer that you see there that's all in orange, almost like a big Pac-Man character, okay, in orange. But that's not actually it, okay? The orange represents nitrogen. Nitrogen molecules make up our atmosphere more than any other gas molecules, 78%. So you may be asking yourself, well, where do we get nitrogen and what do we use it for? Well, honestly, we don't use nitrogen at all. Where does it come from? It comes from volcanic eruptions, decaying matter. When things die, nitrogen gets released in the atmosphere. Volcanic eruptions will send nitrogen up into the atmosphere. And again, the Earth's gravity just keeps a hold of these air molecules while you have the atmosphere in the first place. Keeps it all together. But our bodies do not use nitrogen. Plants will use nitrogen, but they call it nitrogen-fixing bacteria, where they can actually, which hooks to the roots of the plants, which allows them to get nutrients from the soil. But after that, nitrogen really isn't used that much. So the most abundant gas in our atmosphere is nitrogen, and we don't use it, really. It just kind of sits in our bodies and really doesn't have much of a purpose. So nitrogen is the number 1 answer. This next section that's purple here is what everybody thinks to be true, and that's the oxygen. So oxygen makes up 21% of our atmosphere, so it's the second most abundant gas. So if you are good at math, if you take the 78 and you add to the 21, you get 99. So 99% of our atmosphere is made up of nitrogen or oxygen molecules. Okay, I'm not saying atoms, because they're not. They're molecules that bonded together. So an oxygen molecule looks actually, and you're going to see it when we do ozone, is 2 oxygen atoms bonded together to make the molecule, O2. That's what oxygen is. So oxygen, oops, keep pushing that marker. Oxygen comes from plants. We just talked about the symbiotic relationship. Plants give off oxygen, take in carbon dioxide, make food for themselves, release the oxygen. We take the oxygen and release carbon dioxide. So oxygen comes from plants. That's our best producers of oxygen. So areas that are polluted or areas that the air quality is very poor, problem is there's not a lot of plants in those areas, so that's why the air quality is as bad as it is. So I said there's a top 5 answer here, so which means 1% or less than 1% is made up of the other 3 gases that are on this list: carbon dioxide, which we don't want that number to get any higher because it's a good balance right now of the amount of heat, because carbon dioxide is a greenhouse gas. It traps the heat from the sun. We'll talk more in detail about that again. I've talked about it. That's why Venus is the hottest planet, because of all the carbon dioxide in its atmosphere. It traps heat like a greenhouse does. Argon, just one of the noble gases in the periodic table. Well, there's a molecule of argon. And then look at that last step, water vapor. Water in gas form makes up less than 1% of our entire atmosphere. Now you might be saying to yourself, but we have water everywhere. There's water always in the sky. It's what gives us our clouds. If the entire Earth is cloud cover, how can water vapor make up less than 1%? Well, a couple of reasons. One, the atmosphere we're referring to, the one that interferes with us, is actually a very thin layer that surrounds the Earth. There's other layers on top of the one layer that we're closest to. And two, water vapor changes. It changes to water when it rains or snows. It precipitates. That's not vapor, that's liquid water. So it's not a gas anymore. It's liquid water. So water vapor kind of holds at less than 1% because it's constantly changing. It's not always there. Sometimes it is, sometimes not. You go outside right now, it's a clear sky. There's probably very little water vapor in the air. And we're going to have tools that will actually measure how much water vapor is in the air. But it's a cloudy day, it's supposed to storm. There's a lot more water vapor in our area, localized, that is in our air that makes up our atmosphere. So water vapor is always, it's fluid. That's not a pun. It's always changing. So now that you know what the atmosphere is, the fact that all around you are molecules of nitrogen and oxygen and water vapor and carbon dioxide and argon, now that you know that all of these gases exist around you, meteorologists will use air pressure to kind of indicate changes in weather. It's the best tool, the best way to measure changes in weather is by finding the air pressure of a certain location. Because what we're going to get into is the idea of what air pressure is, why there's more in some locations and less in others, and then again, if air molecules are taking up the amount of space that's around you, what other type of molecules are also taking up that space? And that's going to be an indicator of the way weather is going to be. So it all ties into what we're studying in meteorology. So before we can get into all of that, we have to discuss what is air pressure. Well, air pressure is really easy. So as you know, gravity's pulling everything to the surface. All right, gravity has a hold from the core. It keeps you on the ground. It keeps all your books on the table. Okay, so it has an influence on all types of matter. Now, saying that all types of matter means air molecules are a type of matter. Therefore, it is also gravity is also affecting air molecules. So air pressure is going to be the measure of the force, which in this case is gravity, with which air molecules push on a surface. So the amount of air molecules that are around you is actually different in different locations around the world. If you go somewhere that's higher in altitude, you have less air molecules. If you go somewhere that's lower, close to sea level, there's more air molecules. It'll be all because of gravity. Gravity's going to pull as much as it can to the surface. And the farther away from the surface you go, the less air pressure there's going to be. So I'll explain that in detail here on the next couple of slides. But let's get you the definition first of what air pressure is. The measure of the force with which air molecules push on a surface. So in this case, the quantity. How many air molecules are there in certain areas? More or less in certain areas. In order to better understand the idea of the influence of gravity and air molecules, let's take a look at this picture. I took this from an older textbook. I tried to find a newer version of this picture, but this was the best one because there's something specific that I really like on it. It really will demonstrate my point. So take a look at this following picture. Okay? Look at the facial expressions of the woman on top of the pyramid and the cheerleaders on the very bottom. They're different images, aren't they? So the facial expressions are very different. That's why I liked this picture. It looks as though the people on the bottom are struggling and the woman on the top is not feeling a lot of pressure. Wouldn't you agree? If you take a look at it, you've got a woman at the top of the pyramid, and then you've got three cheerleaders, men and women, at the bottom of the pyramid. They don't look like they're having a good time at the bottom of the pyramid. Why? Well, I would not either if I had three people sitting on top of me. Okay? So that might be part of the reason. Doesn't know about why. So think about it. Gravity is pulling everything to the surface. So the higher you get away from the surface, gravity is going to have an influence on you to try to pull you down to that surface. So if you're the bottom part of this pyramid, you're feeling the majority of the weight, let's say, of the objects that are above you. That includes the air. Okay, there's always gravity pulling down air molecules on you at all times. You don't feel it or notice it because you're used to it. It's been doing it your whole life. And if you've been in one location, one area for your whole life, then you've experienced the same thing because the air pressure doesn't change all that frequently, or the amount of air pressure doesn't change that frequently. So the people in this picture is a really good indication of air pressure. The people on the bottom are feeling the most pressure because the gravity of the three people above them, the weight of the three people above them, which is based on gravity, is also being pulled downward on top of them. So the weight of the cheerleaders that are at a higher altitude are being pulled down on the bottom. So the farther on this pyramid you go, the more pressure you're feeling from the weight of the other cheerleaders. Okay. Same idea happens with air pressure. So air molecules have the same reaction. It's going to be greater towards the surface than it is the higher up you go. So take a look at this picture. The higher in altitude you are, the less air molecules that are around because gravity is pulling the majority of them to the surface. So I like this picture just for the fact that it kind of shows you different elevations too, because that's going to play a role into it as well. If you look at the picture on the right, you see the surface around here, okay, and then you see the atmosphere around here. There's a couple of mountains here too, and the indicator of these air molecules showing you the quantity of air molecules, therefore the air pressure, that's being displayed at each of these three sections. So you've got fewer air molecules the higher up you go, and you've got the greater amount the closer to the surface you get. When you have more air molecules, the pressure is considered higher. When you have less air molecules, the pressure is considered lower. Sorry for the bell, and you're going to hear noises in the background. I'm just doing this, again, from the hip, not changing it. Okay, so in essence, here's a relationship between air pressure and altitude. The higher in altitude you go, the less air molecules available, so therefore the lower the air pressure. The lower you go, the closer to the surface, the lower in altitude you go, the more air pressure, the higher the air pressure because there's more air molecules that are present. That's another one of those relationship questions I was asking you about temperature and altitude earlier. With air pressure, higher you go in altitude in the air, in the atmosphere, the less pressure there is. The lower you go, the more pressure there is. So higher and lower pressure. Higher and lower pressure are going to come into play, especially when we start talking about winds and global winds, and why are there global winds, and why does air move around the surface of the Earth. We'll get into all of that later. One of your key terms in the glossary is barometric pressure, which is pretty much the same thing as air pressure. So I wanted to give you a definition, but I also want to play in the tool that meteorologists use to measure air pressure. They use what's called a barometer. A barometer is a device that measures the amount of air molecules in a certain location. So I don't know if your parents or grandparents have ever had a barometer in their house. Schools sometimes have them, sometimes they don't. I've never really found one that's been super accurate to actually use in my classroom. I think we have a few in storage. I have to see if they still work. Anyway, what this device does, this barometer, which is pictured on the right-hand side there, the barometer is a device that's used to measure air pressure. Now, take a look at this. The way this barometer works is when the pressure is higher, look at the weather. It seems to be nicer, doesn't it? Fair, very dry. And then as the barometer goes to the left, change, rain, storm. So the lower the needle is on a barometer, a lot of times a good indication that storms are coming, or it's a good day for a storm to happen, or rain, precipitation of some sort, or snow. As the pressure moves up, that's where the change comes in. So it's either really low or really high. So high pressure has an association with nicer weather. Low air pressure has an association with rainier weather. So now the question becomes, why is that? Well, it really is, what fills up our air? We said nitrogen, we said oxygen. So we have air that fill air molecules that, those types of molecules, the oxygen, the nitrogen, the carbon dioxide, all of those gas molecules are all filling up our air. But there's another one of those gas molecules that's filling up our atmosphere, water vapor. Water essentially is what else fills up our atmosphere. So around us we have air and we have water at all times. The more air there is, the less water there is, because there's no room for the water to be there. That's why on higher pressure days, which is more air molecules, you have nicer days, nicer weather. The pressure is high. If it's rising, it means it's getting high. It's getting nicer. And then if you have low pressure, less air molecules, that gives room for more water molecules to form, more water vapor to fill up our atmosphere. Okay, water vapor is just like air molecules. It's see-through. Okay, it's there. You just don't see it. But on those days when you've got more water in the air, that's going to give you different types of precipitation. Could be snow, could be rain, depends on temperature that causes those. So air pressure and a barometer is a great tool to measure how much air is there and how much water vapor is there, and those two will compete for space. And that's why the needle's kind of showing you that when it's higher on the needle, more air, nicer days, less water vapor. Colder days or rainier days, not colder, rainier days, the needle's lower and there's more water vapor in the air than there is air molecules. Okay, and you feel that. If you go outside and you feel it just feels wet, even though it hasn't rained, okay, that's humidity. We're going to get into that. What that is when we get to water in the air later on. So this unit is broken into the air and the water in the air, and that's the two sections. And the water in the air is what's going to cause weather to occur. So now we're going to revisit our questions from the activity that you did before you started watching these notes. Because now we're getting into altitude, relationship of altitude and temperature. So remember the questions? How does temperature change as altitude increases? And what would be a good relationship statement to make for temperature and altitude? Now we're getting into a different relationship. We said before, air pressure. The higher in altitude you go, the less air pressure there is. So is that the same for temperatures? The higher you go, the lower the temperature, which means colder versus hotter. Okay, we're going to get into that idea. We're also going to get into the idea of temperature versus heat. Like for example, if you go to an area that's got a fire and you feel the heat of the fire, you're feeling the air molecules come in contact with your skin, and the heat is transferring from those molecules to your skin. So with temperature might be high, but you might not feel hot because those molecules those high temperature molecules, they might not be hitting you or coming out of you. There's a difference between heat and temperature. It's a little bit of a revisit from when we did energy back in physics. So we'll make a connection to the physics unit that we did earlier in the year. So the activity you did had you create a chart. The chart should look very similar to the one that's on the screen now. Okay? Air temperature is going to vary as altitude increases. So imagine this as the bottom surface. Let me change my color here. This is going to be the surface of the Earth where I'm circling. Okay? And the higher up in altitude you go, okay, the farther away from the surface you get. That's why that starts at 0. And you go higher and higher in altitude, 100 kilometers upward, basically. Okay? Air temperature reacts different than air pressure does. It's a varied relationship. There's no indication that says the higher you go, the colder it'll always get. Now, that does happen. It does get colder in certain layers of our atmosphere. It does get colder the higher up you go. But sometimes it doesn't. Sometimes the higher up you go, the warmer it gets, which is kind of odd, but this is why meteorologists have created different layers of the atmosphere to kind of indicate temperature changes. That's the whole reason. So temperature varies, as that's your relationship, the answer to your relationship question. Temperature varies as altitude increases. Depends which layer you're talking about. In the layer we're closest to, yeah, it decreases. In the next layer above that, it increases. We'll explain why in a little bit when we talk about the layers. The next layer beyond that, it decreases even more and becomes the coldest layer. But the layer that's closest to space actually gets warmer. The higher or the closer to space you get, the higher in altitude you go. So temperature varies as altitude increases. There are a few reasons, like I said, which will become clearer as we break down each of these layers. In the activity, they asked you to kind of map out the different layers based on temperature. So hopefully you got a chance to do that. In order to understand the reasons why temperature varies, we have to explain the layers in greater detail. So this picture is a picture of the layers of our atmosphere, from the surface to space. So they broke up, and you did as well when you were mapping out the different temperature ranges. You broke up, or they broke up, layers of the atmosphere into different, at least 5 different layers. There's another layer that sits within one called the ionosphere. It sits within the thermosphere. I might talk about it, I might not. I don't know for sure. We don't really need to know it. These are the 5 basic ones I want you to learn. Again, reading it from bottom to top. The surface is the bottom, space is the top. So we need to start with the layer that's closest to you. Well, that's going to be the troposphere. So the next slide is the troposphere, which is one of your key terms. So the first bullet here, I basically put a definition for you for the troposphere, because like I said, it's one of your key terms. The troposphere is the layer you live in. It is the layer that you're going to spend your entire life in. Unless you decide to travel into space, you're going to spend your entire life in this layer of the atmosphere. Okay, it is the lowest layer. It is the one that surrounds the Earth's surface. Some facts about the troposphere is the fact that it's the densest layer. Why? Dense means how much material is making up that amount of space, how much matter in a certain amount of space. Since gravity is bringing all of those air molecules down to the surface, it's going to have the most air molecules and water vapor molecules, therefore it's going to be the densest layer. Gravity is what causes it to be the densest layer, because it's got the most material, the largest quantity of material or matter that's going to be there. Okay, the entire atmosphere, as you see, the atmosphere being very big. Almost all carbon dioxide, water vapor, clouds, air pollution, weather, and life forms are found in this layer. Weather only occurs in this layer. I'm not saying winds don't. Winds do occur in the other layers too, but weather all occurs this layer. It's going to rain, it's going to snow, sleet, or whatever. It's all going to occur in the troposphere. There's no rain that comes from the upper layers that comes down and hits us. The cold air might from time to time, but that's it. Just these things. That's because clouds are always involved. Air pollution. Okay, air pollution does not stretch above the troposphere. It basically stays within this layer. Problem is, that's the layer we live in, so that's a problem. It's tough to send it to the other layers, and it won't go. Whether life forms, again, unless you intend to travel to space in your life, you're going to spend your entire life in the troposphere. And that's true when you fly in a plane. Plane flight usually only gets about 35,000 feet in the air. That's not really getting into the stratosphere. It kind of stays within the troposphere. It's just, the higher level of the troposphere, but it usually stays, plane travel usually stays within the troposphere. Now, question I want to kind of pose in the troposphere here, and it's got to go back to air pressure. Take a look at the picture. I've got a grassy farm with a barn in the bottom part of the picture, and then I've got snow-capped mountains in the distance. So in the picture I'm showing you different areas of elevation. So the question I pose to you is, why do the mountains in the picture have snow but the farm doesn't? Why is it a nice sunnier, warmer day at the farm than it is on the snow-capped mountains? Which means temperatures are different in altitude too. We talked about that, temperature being different. Okay, so the higher up in altitude you go, the colder it can get in this layer. So as you saw in your graph, as you go higher in altitude, the colder it gets. So in elevation, that's true too, because elevation is taking you away from the surface. It's getting you higher and higher. The surface is getting higher and higher. Okay, top of a mountain is much different than an area low to the ground. When you live either at the ocean or you live in Boyertown, you're at a different elevation there too. Okay, at the ocean level, that's called sea level. And then here, we live a few thousand feet above sea level. So you'll start hearing those terms. those types of areas give you different types of precipitation, different types of temperature, therefore different types of heat, and therefore different types of weather. So that's kind of a brief introduction to the fact that when you go up in elevation in this layer, the colder it gets. Okay. So now we're getting into the next layer above the troposphere, and that is going to be the stratosphere. The stratosphere is the layer above the troposphere. And that can be your definition if you want it to be. It contains something called the ozone layer. So we're going to talk about the ozone layer. What is the ozone layer? The ozone layer is actually the layer that actually protects us from the harmful ultraviolet radiation of the sun, which is good. Okay, if the ozone layer did not exist, then there'd be a lot more cases of skin cancer on the earth for people. Okay, we've adapted to accept the protection that the ozone layer gives us. Now, in the ozone, what is ozone at all? It's a molecule, just like gas is a molecule. So this is going back to when we were talking about, hey, what molecules make up our atmosphere? Look at the left picture. That's an oxygen molecule. 2 atoms of oxygen make up an oxygen molecule, O2. That's breathable oxygen. That's what we need for survival. That's what we take from the atmosphere all the time for survival. Take a look at the ozone molecule, which is on the right. Ozone's chemical formula is called O3. So which means it's also oxygen atoms. But it's 3 of them, not 2 of them bonded together. When oxygen atoms bond themselves together in 3s, it is not oxygen and breathable oxygen. It's actually ozone. And ozone is actually a pollution. So when cars produce ozone here at the surface, it's actually a deadly gas. It's not something we can take. Even though it's made of oxygen, the way the chemical formula is bonded, or the way the oxygen atoms bond together, is actually poisonous to us. So it's a very good thing that the ozone layer sits at the very top of the stratosphere, that layer that's above the troposphere. But what it does do is absorbs the ultraviolet radiation from the sun, and it actually protects us. Now, years ago, there were certain types of things, aerosols, and the burning of, not cardboard, styrofoam, that released a gas called chlorofluorocarbons, CFCs. Now, these things used to destroy ozone, and there were areas that were concerned that the ozone layer was depleting in the stratosphere because of the burning of these chlorofluorocarbons. Well, ozone has gotten better. It's actually healed itself. It's actually still protecting us, but there's certain areas of the Earth that are not covered with the ozone layer. Antarctica, to be specific. The ozone layer on Antarctica is actually very depleted. So there, you really need to take protection from the ultraviolet radiation of the sun, because it can, like I said, create skin cancer very easily. So ozone layer is that layer. It's at the upper part of the stratosphere, and what it does is absorbs the sun's energy because it's absorbing the ultraviolet radiation. So in that case, temperature should be increasing, shouldn't it? Since there's a top layer, the upper layer of the atmosphere that's actually absorbing energy. So therefore, in the stratosphere, you see the temperature start to increase the higher in altitude you go, because there's a layer that's absorbing a lot of that sun's energy. Okay, converting it to, well, I don't think convert it to heat, but at least increasing the temperature. So therefore, the stratosphere, as you increase in altitude in the stratosphere, the temperature actually increases because of the absorption of sunlight by the ozone layer. So the ozone layer helps to do that. Oh, I just got to explain that. Why would this layer get warm with altitude? Because the ozone layer is up there absorbing the sun's energy. Okay, next layer is the mesosphere. Not much to say with meso. Meso just means middle. So if you've got the 5 layers there, as you see this picture, the mesosphere is the middle layer. So the mesosphere is, like I said, the middle layer of the atmosphere. It is the coldest layer, and you saw that when you did the activity, that the temperatures dropped a lot colder than the troposphere did. Contains large windstorms, too. Their winds can travel above 300 miles per hour, kilometers per hour in that layer. So those are our 3 facts for the mesosphere. Not much else to say about the mesosphere. It's actually kind of boring, but it is up the upper layer. But as altitude increases, temperature decreases, so much so that it is considered the coldest layer. Now that's going to change when we get to the next layer, which is the thermosphere. The thermosphere is going to be the layer that's a large layer that's above the mesosphere. So it's the uppermost atmospheric layer. Now, in this layer, you've got nitrogen atoms, you've got oxygen atoms, but they're few and far between. Why? Because you're the furthest away from the surface. Okay. However, this is the layer that is receiving the sun's radiation first. So those nitrogen atoms and those oxygen atoms will absorb the sun's energy on a regular basis, even though they're few and far between each other. And what that does is creates what's called the ionosphere, okay, turning these atoms to ions. We talked about that with comets. We talked about that before in energy. All right, that layer is considered part of the thermosphere, but just the idea that the upper atmosphere. So in this case, as altitude increases, this layer temperature increases as well. That's why it varies. So like I was just talking about the ionosphere. What is that? Well, those nitrogen and oxygen atoms are turning into ions because the sun's radiation is causing them to do so. Turning an atom into an ion. Not something I need you to memorize right now. Temperatures are increasing as altitude increases because molecules will absorb solar radiation. Now, here's the difference between temperature and heat. Heat requires a transfer of energy, which means touching. Molecules have to touch each other in order for heat to transfer from one molecule to the next. The temperature may increase in this section, but that doesn't mean there's heat in the thermosphere. There is not. Because these molecules are so spaced out from each other, the molecules, there's not a lot of heat in the thermosphere. There's higher temperature because of the absorption of the sun's energy by these molecules, but there's no heat because they're not coming in contact with each other. So if you go into the thermosphere, which that was actually physically possible, it would technically, temperature might go up, but you might not feel, unless you're getting the sun's direct radiation, you wouldn't feel it from the air molecules. Air molecules wouldn't be able to touch you. Why? Because there's not a whole lot up there. So because they've all been pulled towards the surface. So there's very few molecules up in that thermosphere. So just because I say something's got a high temperature does not necessarily mean it's hot. Because in this case, it isn't. Oh, I do that all the time. I always jump the gun on this. So again, just to kind of reiterate my point, remember from physics, heat transfer requires contact, and the molecules are few and far between that they don't contact each other. So let me show you a picture again of those layers. Troposphere, you got the most air molecules. Stratosphere, you got the ozone layer at the top, but you've got, fewer molecules than the troposphere. Mesosphere has even fewer molecules. I showed a picture of a meteor being, destroyed in the mesosphere. And then the thermosphere, look how far apart those molecules are, and that's just an assumption. Okay, they're so far apart from each other that they don't come in contact. So there's no heat up there. There's temperature, but there's no heat. Those molecules that are up there are absorbing the sun's direct radiation and causing temperature to rise in that location as you go in altitude because you're getting closer to the sun. But no heat is being transferred from one thing to another because those molecules are not next to each other. The last layer is the exosphere, which is pretty much the space layer. It's the thin, that's what we call the lower Earth orbit when we talk about satellites. So it's still technically part of the Earth. It's technically some gas molecules that are part of the Earth's gravitational pull, but it's very few and far between even. But we do acknowledge the exosphere is a layer of the Earth's atmosphere that this is where usually a lot of our satellites are found. When we talk about low Earth orbit of our satellites, they're usually found in the exosphere in this section. So those are the 5 layers: troposphere, stratosphere, mesosphere, middle, thermosphere, exosphere. Those are the 5 layers. That's a breakdown. As you go up in altitude, pressure decreases. As you go up in altitude, temperature varies. Troposphere, it goes down. Stratosphere, it goes up. Mesosphere, it goes down. Thermosphere, it goes up. So the temperature varies depending on which layer you're talking about. The whole reason for 4 or 5 different layers is because of the changes in temperature. So that concludes for now the layers of the atmosphere notes for the meteorology unit. What we'll get into next is the global winds, and that'll be the next set of notes.